Make sure you write your name in here. There's my name. And then today's date is 4/16/24. Okay, great. And here's a lot more information about ordination, why we use it, what kinds of things we can ordinate. And again, that it's not hypothesis testing. And we're going to make some cool graphs. And these few graphs here basically show the same thing that I showed you in the lecture. Just if you had one species on an axis versus two species, you could have two axes. But then when you try to do it with three species on three axes, it gets more complicated. And then you really can't do four. You just can't do four. But what I want you to see now, it takes a long time. Hello. Scroll down. Okay, there it gets complicated. All right. Our questions here are, how can we classify snack foods based on nutritional data? And what nutrients best differentiate different categories of snack foods? Right? So to collect data on snack food, you got to have a snack. And if you don't have a snack, you can go online and you can find a website that gives you a snack. Well, I'm just going to go on through and I'll record this and I'll send it to you if you need to do it later, because we've got half an hour before the end of class. All right, now to install the necessary packages, we're going to need to install dplyr, because the first thing we have to do is filter the data for the healthy and unhealthy snacks. We got to call them healthy snacks and unhealthy snacks, and then get the means of the nutritional information, and then bind all that into a summary table. That's what that chunk does. And then we can see here for our healthy and unhealthy snacks, here's the mean calories for healthy, 309, unhealthy, 345. Fat is a little bit lower in the healthy snacks, it's lower sodium. Healthy snacks have higher fiber, but our healthy snacks also have a lot more sugar and a lot more protein. Interesting. But we're not going to do a hypothesis test. We're going to see how they group together. And here we talk more about what NMDS and PCA are. We need to load this package. If you haven't already done it, load this library vegan package. And then we need to prep the data. Now, for the PCA analysis, our data can only contain numbers. We got to get rid of our names, everything else. We can only have numbers, and it has to be stored as a matrix. So we need to first extract the numeric variables, and then we save it in something called snack data numeric. It still has the calories and fat, but it got rid of our healthy, unhealthy, and our names. And then we can make our data into a matrix format. Just run the code, it should work. And then we're going to install this, we're going to load this Factominer library, and we're going to run the PCA analysis. And one thing that's cool about this is we right away get these neat graphs. The first graph, if you click on the one on the left, it shows you each one of these is a snack. It's a different data point, right? So we're like, right away, do we see healthy, unhealthy, really grouping into two groups? I don't. I wonder what number 9 was. That's different than other things. I wonder why. Let's look over here on the second graph, because this shows us the loadings. And this is kind of interesting. Even though we're not seeing too strong clusterings, we are seeing that this the first PCA axis is strongly defined by snacks that have a lot of calories, a lot of fiber, a lot of protein, and a lot of fat. So the interesting thing on this PCA graph of variables is that you right away see also that sugar and sodium are orthogonal to each other. They're opposite, which is, yeah, not surprising if you think about it. There are salty snacks and there are sugary snacks. And if you think about it, when you walk into a store looking for a snack, you often think to yourself, well, do I want something sweet or do I want something salty, right? So sugary and salty are different from each other. and different from this whole calories, protein, fat, and fiber. So what do we learn from that, right? Well, first of all, it looks like I'm not seeing a big difference in nutritional value. Our nutritional value is not differentiating snack type in any obvious way according to this graph, but it does seem like these different axes of variation are orthogonal to each other. So salty snacks and sugary snacks versus, this other axis of calories and protein and fiber. And that this first dimension, right, it's explaining about 51% of the variation. And that's the PCA1, and the PCA2 dimension is explaining about 20% of the variation. So print summary of the PCA. Let's print the summary of the PCA. Now, when you look at this, that's a lot, right? That's a big chart with all these eigenvalues. But all this is saying, here's the amount of variance that's explained by dimension 1, the amount of variance. And here's the percent of the variance, and then the cumulative percent of variance. So if you added up all of these variances, it would be the total variance in the data. And if you added up this total percent of variance, it would be 100%. And notice each one of these dimensions is a different variable: calories, sugar, fat, right? And we have as many different dimensions as we have variables. And then the cumulative percent of variance, right? So the first axis explains 50%, and then the second axis adds another 21% for a total of 72% of the variance. And then the third axis adds 12% for a total of 84%. So where do you want to cut it off? It's up to you. And then if you think about here, the different individuals, the first 10 individuals that explain the variance. So the top individual for explaining variance was this number 9, right? This number 9 was explaining a lot of variance. And again, that kind of popped out as looking weird. Like this popped out as looking weird, as something a bit of an outlier, whatever snack number 9 was. I guess we'll see. What's snack number 9? And then how much each one of these factors, these are the loadings that I showed you, how much each one of these factors are contributing to the differentiation of the snacks. So calories, fat, sodium, fiber. It looks like fat contributes quite a lot to the differentiation of the snacks, but also does fiber and protein. So these are all on axis 1, right? And then sugar actually doesn't contribute that much, and sodium doesn't contribute that much. It's on that second axis going up and down, right? But we get a lot of output, right? It's already like, wow, that's a lot to digest. I thought we were simplifying things. But it's simpler than having all those different variables. Now we can think mostly just about PCA 1 and 2, because that gives us the majority of the variance. Here's another way to graph it. This next one graphs the results using a heat map. So you can see kind of how in this case, how calories is really separating out the different snacks. And so number 9 must have been a really high calorie snack. And then the lower calorie snacks are coming up over on the left side. And here's another way of looking at it, which might be familiar to anyone who's done any kind of phylogenies. So first we're going to look at cluster analysis and dendrograms, another way of kind of grouping up these snacks. And first we calculate the Bray-Curtis distance. This is the metric that is used to calculate how different the different snacks are based on the data that we gave it. And then we perform a hierarchical clustering analysis, which just kind of goes on under the hood. And then I'm going to make a vector of the snack names so we can label them and see what they look like, see what's what. And then finally, we create a dendrogram. And yeah, we're used to looking at species like this, right? You've seen species on a dendrogram and how species are related to each other, or could be even varieties within a species. Now we've got a family tree. We've got a family tree of our snacks. What snacks are related to each other? And if you look, here's our first higher split here on the left. These are chocolate, pistachio nuts, Cliff Bar, etc. And then we've got all of our yogurt, chewy bars, crackers, beef jerky, power bars. I don't know. I'm not seeing like healthy and unhealthy separating out really clearly here either. What can we tell from the dendrogram? Well, snacks that we consider healthy versus unhealthy seem to be clustering together. Because, I mean, here we've got dark chocolate, pistachio nuts, Cliff Bar. This is kind of the healthier snacks. Mango, Swiss cheese, trail mix, Arari, maybe that's on the border. And that's showing up here with Lay's baked cheddar chips, which I would definitely not count as a healthy snack. I'd say that's a yummy treat, but not a healthy snack. And we've got granola bars and protein bars, goldfish crackers, Tostitos, and Cheez-Its all grouping together. They don't really look like they're, so based on their nutritional content, they're similar. So if what you were really looking for wasn't a healthy versus unhealthy, you're like, well, based on the actual nutritional content from the label, all of these snacks are not really different from each other. These aren't different from each other. These are all pretty similar. Well, how different is different? We are not hypothesis testing, but we can say they're kind of a continuum. Maybe that's the answer. So what can we infer from the dendrogram? I just talked a lot. You guys can think about it, answer that. And then we can also do another kind of analysis. This is the NMDS analysis. And it gives us something pretty similar. Something pretty similar. Again, here's our snacks. It looks, well, it looks a little different. Maybe because that the PCA was strongly driven by whatever number 9 was. Wait, what is number 9? Let's look at our 9th snack on this list of snack data. Snack data, oh, that's our numbered one. We want the one with the labels on it. Okay. Goldfish crackers. Calories didn't seem that different. Fat. Something's weird here. Oh yeah, something's weird. Hey, Kaleni, I think you made a data entry error here. I think that's why these are showing up as so weird. I don't think that goldfish crackers, although they are salty, are 191. And I think yogurt also, you guys, we got to either take sodium out or do this right, because this is not how many grams. Remember I said you got to convert to milligrams. So let's go back. Let's go back to our data. Okay, now when we do the PCA analysis, what do we get? Well, it's not like we get the right answer, but we get a different answer. We get a different answer with our data now. We're still not seeing any clear clusters. I want to see 2 groups. I want to be like, these are the healthy snacks that I can feel good about eating, and these are the unhealthy snacks that I can judge other people for eating or feel guilty about at night by myself. Haha, Doritos. Right? I'm so good all day long. I just ate apples and then at night. Okay, so what are the variables of note? Not that different still, interestingly. Sugary snacks are still coming out on one end, and sodium and protein on the other end of the second dimension, but that only is 30% of the data of the variability. Actually, interesting now, look at the first dimension is explaining about, get that so you can see it. The first dimension of the PCA is explaining roughly 35% of the variation in all the data. And the second dimension is explaining roughly 30%. So these two axes have not equal, but similar importances. And this can happen sometimes. I wonder what the other dimensions explain. So again, like high calorie foods, high fat foods, they go together, right? It's got a lot of calories. It probably has a lot of fat because fat has a lot of calories. Sodium and protein go together. Those, high protein snacks tend to be the salty snacks. The sugary fiber, not exactly together, but a little bit closer, probably because the fruit has high sugar and also high fiber. Let's see, what do we learn from this? Okay, so you can write new answers since we learned new things from our new data. Let's rerun this PCA summary too. And again, we're finding that our different dimensions are explaining, we have what, 35%, 30%, and then 17%. So to really explain about 82% of our data, we actually need those first three dimensions. Otherwise, we only get about 64% of the variability. It's not an easy data set to understand, is it? Yeah, and now we can also see that calories and fat and fiber are the three variables that are explaining most of the variation in our snack foods. And then we can look at our PCA loadings here. And it's really putting calories as the main thing differentiating them, because if you see again, well, actually, I don't know what I could have done with that here. Why did it choose calories? I think it could have used fat, but similar. The high calorie foods are over here on the right. The lower calorie foods are sort of over here on the left, but there's a continuous gradient. There's not like these are the high calorie, these are the low calories. If I had made up the data, I could have chosen things that I thought were going to be different, but I thought it's more fun to look at real data and be like, based on nutritional content, can we really easily classify foods as healthy or unhealthy? Just based on the data that they give you on the label. Here's what they're telling us. How does this help us? And if we look at our cluster analysis, we calculate the Bray-Curtis distance, and we make our dendrogram with the snack labels. Okay. And I know I was kind of smushed. I wish it was like longer. It'd be easier to see. But now, are we seeing anything that makes sense? Okay, a little bit. We have yogurt, strawberry ice cream, and craisins kind of go together. There's like sweet, kind of healthy things. Dark chocolate, pistachios, barbecue chips, and Swiss. Yeah, this kind of like really high fat foods, cheese, granola bars. Yeah, it seems like these are kind of like the lower fat foods and then the higher fat foods. And then these are the like high protein foods over here. Well, no, that doesn't make sense because mango's in there. It's still hard to really get a grip on what's going on here. What can we infer from the dendrogram? Anybody else see any good patterns that make sense to them? Crackers, trail mix, Doritos. I'm feeling better about our data, but the results are still really hard to interpret here. What about if we do the NMDS? Let's see if that helps us. Still not seeing any clear patterns. Okay, now we're going to code them by what we thought was healthy versus unhealthy. What a mess. It's all over the place. So what we think is healthy versus unhealthy apparently has no relationship with the nutritional data that we have. Assuming we got it right this time, and assuming that these are right. But why'd you say craisins were an unhealthy food? Who got craisins? Who said those were unhealthy?
I had craisins, but I put them as healthy, I think.
Huh. Did something go wrong with our data?
So is healthy.
But with the lowercase h?
Yes.
Yeah.
Sorry.
That's why. Wait a minute, Emmeline, Cheez-Its really healthy? Uh, one thing I love about this is how it's so real. It's so real. Um, what else came out funny in that graph though? There was something else that came out really funny in that graph, and I was like, that shouldn't be. Strawberry. Yeah. Yeah, Cheez-Its says she category. Okay, healthy. No, somehow that came out as unhealthy. What's going on with my code? Okay, what am I saying? Text displays if else category equals healthy, then green, otherwise red. Oh, so if it says healthy with a capital H, it goes as green, otherwise red. Anyway, class is class is going over. What did we learn about our plots? There you go. That's what we learned. We've learned that we just have no foods are not really healthy or unhealthy based on what we think is healthy or unhealthy. And if looking at nutritional content, it's a gradient. The gradient. Thank you all so much. I'm going to close this out. I think that was fun. Am I the only one who thought that was fun?
Thank you. Have a good day.
Thank you. You have a good day too.